So right now we're going to have two shorter talks. The first one is by Carla Crucianelli about interacting particle systems on sparse W random graphs.
Okay. Thank you very much. Well, as Roberto said, my talk is Interacting Particle System on Sparse W random graphs. And this is a work that I've been doing with my PhD advisor, Ludovic Tangpi, and I'm going to get going. So essentially, what we're going to talk about, so the classical question is, in general, in interacting particle system is, does the system will tend to something when we take the number of particles to go to infinity? And there are a lot of classical results in the mean field case, which is in the case where all the particles are interacting in a symmetrical way. So essentially, all the interactions are dealt in with respect to an empirical measure term. But what happens if we don't have this as a case? So instead of having an empirical measure, we have other thing. So that's the first part of what I'm going to talk about. So what's the problem that we're going to discuss? And this is going to be setting the particle system on a graph that we're going to consider to be a random graph. The second part will be about what's the large population limit, what happens when this goes to infinity, or what kind of solution we expect for this system to solve. And finally, in one terms, will this converge? So first, let's talk about the setting of the problem. So the classical, a little bit about what's classical to setting this problem on. So consider we have n particles that we are going to index from 1 to n. And we have m-dimensional Brownian motions, also indexed by 1 to n. And we're going to give the initial conditions in terms of these probability measures gamma. So the particle system will satisfy this stochastic differential equation. And in case someone is not familiar with stochastic differential equations, we can think about the sigma being 0. A few of the results will be trivial in this case, but at least to settle some ideas. So in this case, as I said, usually we would consider the mean field case that has, instead of this measure m, to be an empirical measure. But in this case, we're going to consider a weighted empirical measure. So essentially, what we're going to have is this weighting term here that will give the graph structure of the interaction particle system. Essentially, this matrix set zeta ij will be the adjacency matrix of a simple random graph that will just be the interaction of the particles. So essentially, this will be a 1 if the two particles are interacting, and a 0 otherwise. And we allow this to be random, so each of these is a random variable. And beta n will be a non-negative real number that will represent what is called the sparsity parameter on the graph, of the graph. And it acts here as a normalization term. So great, now we have this particle system. We want to say, well, what we're going to propose as our large population limit. And here we will need to consider what it means for this graph to go to infinity. And it's classical in the literature that we need to introduce graphons for this. So a graphon is just a word to say a symmetric and Borel measurable function that goes from the 0-1 interval to the positive reals, non-negative reals. And what is known is that graphons are the limit when we're considering convergent sequences of dense graphs. And we can understand this as thinking that if we have a graph that has a number of nodes growing to infinity, then what we will have is that, in this case, the graphon G will represent a graph on an uncountable number of edges, of nodes, and we will have, so for example, take x and y to be two numbers, and then the weight of the edge between x and y will just be G, x, and y. So in this sense, this generalizes the notion of a graph. So what's the system that the large population limit is gonna satisfy? So essentially now we're gonna consider a graph on G that is related to the graph structure it's related to the graph structure of the particle system. And I'm gonna omit some details here because of time constraints, but we can talk about this later. And we're gonna propose that our system is a continuum of players. And this is of a lot of importance in a lot of economical applications where we want to study stochastical systems that have a continuum number of players. So we're going to index our players from the 0-1, and each of them will carry a Brownian motion. But there's a problem. If we want to consider this set of Brownian motions, we cannot take them to be jointly measurable with respect to the with respect to the usual product space and to be independent at the same time. So what we're going to propose is to use something, to use some extension of this product space that is called a Fubini extension. So to be able to construct this, we need two conditions that I'm going to be fast about this. So with just one integrability conditions and one measurability conditions, what we can construct, and this is a construction that was given by Sun in one paper, and Aurel and Carmona use it for the stochastic, for the sense of stochastic differential equations, we will get that there's a Lebesgue measure, an extension of the Lebesgue measure that we're going to index by I and lambda, and a sample space omega p, and a Fubini extension that is an extension of these two, an extension of these two probability spaces, of the product of these two probability spaces, where we also retain Fubini properties. So we are able to interchange the expectation and the integral with respect to this process. And in this place, we were going to be able to carry a set of Brownian motions that are what is called essentially pairwise independent. We're not going to be able to use pairwise independent everywhere, but this is slightly weaker. And it means that if we take a Brownian motion, then almost surely if we pick another one, they're going to be independent as a pair. So the question here is, what's then the differential equation that the limiting system is going to satisfy? And this is what we will hear. Essentially, this is something that resembles a lot to a McKean-Blas sub-SD, but instead of having the law of the process, we're having a measure nu that is an extension of this, in the sense that here we're weighting using the graphon as a weight to define this measure. And one of the advantages of this is that this is non-symmetrical. So we don't need all the particles to behave the same in this limiting system. And it's actually something that we expect. If we consider a non-symmetrical graph, then, well, why would the limit be something symmetrical? And of course, we're giving measure structure just by using every Borelian. One thing to notice here is that this is not a probability measure because it's not normalized, but it's a positive measure. So we need to use the bounded Lipschitz distance to give all the conditions, because all of our assumptions, because this is going to be the metric that metrizes the weak topology here. So the first question that we need to address at this point is, well, does the solutions of this exist, and in what sense do they exist? Because a Fubini extension is not something that's studied yet, at least. So the first question we propose is, well, under which conditions do we have existence and uniqueness of these solutions? And under fairly mild conditions, because if you notice here, the first condition is just to say that the coefficients are Lipschitz with respect to the second and third coordinates, and the second condition is at most linear growth condition, which are the usual kind of assumptions we use for existence and uniqueness of SDs. And an extra condition about that the two coefficients have to be continuous with respect to the first variable, that is the time. Then we get the existence and uniqueness result. That is, that if G is a square integrable graphon, and then there will exist a unique solution in the L2 sense. And here I'm denoting just the box. It means that it's not the usual product space, but it's this Fubini extension that I'm defining. So great. With all that we said, we have that there exists a unique solution. So the problem is well defined, at least. Then what we need to do is say, well, what kind of convergence do we have? So the first thing that we notice is that the particle system is a discrete system, and the large population limit is a continuous. So we're going to first have to find a discretization of the points that we're going to consider in the continuous case. And that's most of the content of the following condition that we need to assume. So we're going to define the points xi to be just the left intervals, the left extremes of partitioning the 0, 1 interval in n smaller and equal intervals. Then we need to assume that the zetas and the Brownian motions that we constructed are independent, which is reasonable because we can do it in different probability spaces. And then we're going to construct the following graph structure for the matrix, adjacency matrix that I said I was going to discuss in more detail. So essentially, we're going to assume that the sequence of real numbers beta n, that is on the 0, 1, will satisfy that beta n times g on these points xi, xj is smaller than 1, and that n times beta n goes to infinity as n goes to infinity. So finally, how we're going to sample the random variables adjacency matrix is going to be just Bernoulli's on g times beta n. And this is essentially what is usually called a W random graph. I'm not going to go into more details because of time, but that's why that's on the title of the presentation. So the parameter beta n is important in the graph theoretical sense, and it will represent the proportion of neighbors a node has compared to the total number of neighbors, and the condition n times beta n will just mean that the degree of each node diverges. So that's the assumptions we're getting on the graph by putting these formal conditions. And well, the second, I already mentioned it. Finally, we're going to use a synchronous coupling argument that is typical in these kind of proofs. So instead of using the system x, xi, y, system y for the particle system, we're going to define this couple system to carry the same Brownian motions in the points that we defined. Again, we're going to be able to get as a corollary a relation between y and x, but we need to be able to compare the different Brownian motions. So the result that we get is the following. So under all the conditions that we stated, and if the moments satisfy that the n plus 1 moments, and here n, a small n, will just be the dimension of the system we're considering, it's uniformly bounded, and sigma does not depend on the measure, then we have an L1 type convergence over the average over all the points that we're considering. And, and I'm assuming that G is continuous. Continuous can be relaxed. That's to not introduce more hypotheses. But the important thing is that continuous will imply bounded, and that's the important thing that we need to keep if we relax the continuity assumption. As a corollary, as I said, we can compare in terms of the loss of the, we can compare the loss of the particle system we defined in the beginning with respect to the bounded Lipschitz distance, and again, we get a convergence when we average over all the points that we're considering. And finally, we can get an interesting corollary. That is that we have an L1 convergence between the average over the particle system and the integral over the graph on SD that we defined. And what it means that we get is a weak law of large numbers kind of result. And this result is important for two things. Because something that I did not talk up until now is that why is all of this important and relevant? Why do I need to construct these Fubini extensions that I'm omitting a lot of technical details, but it's actually really technical, and there's a lot of details to take into account when we're considering this kind of construction. So the first thing is that the fact that this integral is well-defined is due to the fact that we're working on a Fubini extension. If we wanted to avoid using Fubini extension, and there's a lot of papers doing that, we need to get rid of the measurability, so we don't get this measurability result. So this object is not well-defined. But moreover, the Fubini extension framework is giving us an exact law of large numbers type result, that it means that this integral that I'm defining, this integral that I'm defining here is actually almost surely constant. So this is almost deterministic, and this is something that is that's just also relevant in economics, and there's other papers that also talk about how this kind of integral has to be deterministic, and economical literature deals with this in a different kind of way. But other papers that do these kind of things use a lot of exact law of large numbers type results. So it's important to have a framework that can deal with an exact law of large numbers. So that's. Thank you very much.
So questions? I have one quick question, which is, there's this other framework for graph limits. I mean,
yes,
there are a few others, but
there are a few others. Because of the time, I didn't want to get a lot into that.
Okay.
But yes, there's the I said at the beginning that the graphons are introduced for the dense case,
Yeah.
and the really sparse case is in the weak local sense. But there's also the LP, the LP sense, and that's the one that we want to consider here, that lets you deal with the intermediate one also.
Okay.
But the condition of n beta n going to infinity kind of forces you to be in the middle. Okay. So using any of the others seems it won't work. So,
Okay.
So we're going in the LP sense.
All right. Thanks. Any more questions? Well, if not, let's thank Carla again. And we